In this video, we're going to look at some more electrolytic reactions. And so the previous reaction the previous electrolytic video outlined the difference between electrolysis and voltaic reactions. So electrolytic and voltaic reactions. Several of the examples we gave of electrolysis are recovering elements. So when you have the electrolysis of water, when water is the strongest oxidizing agent, the strongest reducing agent, you can produce oxygen and hydrogen. And so we're covering those elements. When we had molten sodium chloride, that was where we had the sodium chloride as a liquefied form. We had pure sodium ion liquid and chloride ion liquid. And so what we end up getting is we can produce pure sodium and chlorine because we have no water to compete with the sodium ion, which is an extremely weak extremely weak oxidizing agent. We looked at the chloralkali process that you need to be aware of, where if you have sodium chloride solution, where you would have the sodium ions, we'd have chloride ions and water, that we would expect that water would be the strongest oxidizing agent and the strongest reducing agent. But what we find is that water will actually not be the one that reacts, but the chloride is going to become chlorine if we produce enough voltage. And then at the cathode, we still have water that's producing the hydrogen and hydroxides. We looked briefly at the case of the purification of aluminum, where they needed to come up with a clever way to dissolve the aluminum because aluminum has such a high melting point. And so they used this cryolite chemical to dissolve the aluminum oxide, so the aluminum ions become the strongest oxidizing agent and produce aluminum. Now we're going to look at electroplating. We're still recovering elements as a general rule for electrolysis, but now what we're going to do is we're going to coat the chemical onto something. So electroplating happens and it deposits a thin layer of metal on an object, and that happens at the cathode. So the cathode is where you do the electroplating because that's where the electrons are going to be gained. I did a video where I showed electroplating copper. And so I used a different solution than they do here. But in the video, I had copper 2 sulfate solution. And so it has copper 2 ions and sulfate ions and water. And this is going to be my strongest oxidizing agent. And this is my strongest reducing agent. And so what I had was I had copper 2 plus 2 electrons makes copper solid. That happens at the cathode, GrOAC, and I'm producing a thin layer of copper. So watch that video if you haven't. I try to show you the copper being collected. But a way to keep this reaction running is actually if they put copper solid at the anode, and whatever they want to coat, we had carbon here, the copper solid is going to become the copper 2 ions at the anode, and at the cathode, you've got copper 2 plus 2 electrons make copper solid. And so they can use low-grade copper here, they call it blister copper, and then they can purify the copper over here. And so that's a way to purify copper, but it's also a way to keep the reaction running. They do this kind of same sort of electroplating with lots of different chemicals, so it's not uncommon to get cheap silver jewelry. What they do is they put silver ions and then they make silver solid at the cathode, or gold ions become gold solid at the cathode. And so we can coat things in those chemicals. One of the interesting cases where they do this is chroming. So if they chrome plate something, they'll use this chrome 6 oxide in strong acid, and then they place something that is iron to coat at the cathode. And so they've got iron at the cathode, but what happens is the chrome becomes chrome solid, and it coats the whole thing over here. And so this is how they can chrome plate, usually their car parts or something like that. It gives it a very shiny, resistant exterior that is it's attractive, but it's also very practical because it's coating the iron and prevents corrosion. Um, in the electrolytic cells worksheet, I'll get you started here. I'm going to take a look at the cobalt 2 iodide cell, and it says to predict the cathode and anode half reactions, calculate the E net. And then down here for A, B, and C, they want you to sketch the cells. So for cobalt 2 iodide, I've got cobalt ions, I've got iodide ions, and I've got water. Water we know is an oxidizing agent and reducing agent. This could gain electrons, so it's an oxidizing agent. This is a reducing agent. When I go back to my data booklet, if I look for iodide here and water here, I'll see that iodide is my strongest reducing agent. Because water is here and cobalt's here, cobalt is my strongest oxidizing agent. And so what I get is my strongest oxidizing agent, strongest reducing agent. I get cobalt 2 plus 2 electrons makes cobalt solid. And then my 2 iodides become iodine plus 2 electrons. And this is my GR OA, that's at my cathode, and this is my LEO RA at my anode. And then the E cell is still going to be E cath minus E anode. But here now, I'm going to get a negative value. So if I look off the data booklet for my cobalts, my cobalt half reaction is negative 0.28 volts. That's my cathode. And my anode, I subtract, so minus the anode's value. And iodide is positive 0.54 volts. And so my E cell is going to be positive zero, or pardon me, not positive. It's going to be negative 0.82 volts. And so it's a non-spontaneous reaction. If I wanted to draw a diagram of it, I've got a container in here. It's got cobalt 2 ions plus iodide ions. I guess I don't need the plus there really, but the cobalt 2 ions and iodide ions. And we're going to need inert electrodes going into here. Call them platinum or carbon, doesn't really matter. But right now it's got to be connected to an external power source. And so if my external power source, if my positive is here and my negative is here, so this negative one is here, that electrons are going to the negative side. So that is where they're gaining electrons. This is my cathode, and the electrons are going from here. So that's where they're being lost. This is my anode, but it's still my positive side because the external sources say that this side is negative over here, and this side is positive over here. And so because the power source is where the electrons are getting driven from and to, that's why we get the different signs for cathode and anode with electrolytic cells.